Hey everybody, we are down here in the lab with yet another Punchout PCB that doesn't seem to be working. This is another one from somebody on the forums who was having trouble, and apparently it is not booting. So something this drastic, usually you see sprite problems, sound problems, things seem to be working a little bit, but just a little sketchy with respect to graphics and stuff. This one is just simply dead, which actually can be a good thing because usually it's something more global. Rather than trying to figure out why that one particular sprite is, not the right color or something odd like that. So, something like this, what I like to look for, or what I like to check rather first, is the CPU. Make sure it's getting a good clock. Make sure it's getting a reset signal that makes sense. These games, you should be seeing the reset be high all the time because I think they're active low on the Z80 CPU and most of the other CPUs. And these games all have a watchdog circuitry, and basically what a watchdog does is it's just a counter, and it counts up to a certain number, and if that number is met, it'll pulse the reset to the CPU. And why does it have that? They throw them on there so that as it's executing instructions from your program ROM, every once in a while it should jump over to the watchdog and reset it, and then go do some more stuff. Jump back to the watchdog and reset it. I'm pointing over here. Who knows where the watchdog is on this thing? But and the purpose is to just keep things under control. If for some reason the program gets lost in the weeds due to bad connection or a bug, something like that that's going on, it'll get lost somewhere in program, and the watchdog timer will go off, and it'll reset the CPU and bring things back to a steady state. So those are the two things I like to check right off the bat. Do we have a clock? Is the watchdog barking, or do we have a decent reset? Watchdog, I think on the Z80, reset on the Z80 is pin, 46, which is that guy there. And, oh nice, my camera can pick up the logic probe this time before it was sketchy. So you can see that's high, which is good, because that means the watchdog circuitry is constantly getting reset. So that tells me right off the bat that program ROM and addressing that accesses that section of memory, or accesses that that portion of the memory map is working fine. So chances are it's something related possibly to the graphics, and we got two other PCBs to check here. But we'll start slowly. First of all, based on that, and I'll throw the fluke on here just for good measure, but I'm going to guess that part of the circuitry is fine. It's able to access the program ROM, and it's running the actual Punchout program, but for whatever reason, the graphics are not getting dumped to the display here. So stay tuned, and we'll figure this one out. Alright, so pull the fluke out. Got my Z80 pod hooked up to it. And then this is the main source. So whenever I debug a board, I always pull out the main source because it gives me my memory map, and then I don't have to try to figure it out by looking at that rat's nest of a schematic. So, yeah, pull the source and look at the memory map. So the main CPU, you can't see it here, but if you bring up the main source, you can kind of follow along. Here's all your address mapping for the main CPU. You got your ROM, which is your program ROM, NVRAM, non-volatile RAM, regular RAM, video RAM for the opponent and the main character, background, sprites and characters that are going on, and just general video RAM. So with the fluke here, I can run tests on all these different sections. I think in my Tron video you can see I did a sig check on the ROM. I won't go through that here, but you can take a look at that video. But let's say we want to test out one of these sections here, the RAM for example. It starts at D000 to D7FF. So on the fluke here, you can say I want to do a RAM, we'll say RAM short test here, and it wants to know the address range. So we said it was D000 to D7FF. And so what it's doing is it's starting at D000, working its way up to D7FF, and it's writing a value and then reading it back and moving on and writing a value, reading it back. And it may, the algorithm I'm sure is a little more complex than just that. It's probably playing with the bits and some kind of algorithm to ensure that certain bits aren't tied low, data bits, certain address bits aren't tied low, and things like that. If that were the case, it would come back and say, hey, address bit 10 is stuck high or stuck low, or something like that. Or, hey, two address bits are shorted together, or something like that. Okay, so we're okay. So the RAM, at least the address logic to that RAM, according to this, is okay. It can read and write, to the RAM. What happens after the RAM? If that information gets sent out to some other logic that throws characters on the screen, there's no way to verify that with the Fluke. All this does is check out from the CPU to the ROMs and the RAMs, are things looking okay? And a lot of people, when they see these videos or they see guys using a Fluke to solve problems, they think, man, I got to get one of those, then I'll be able to debug boards and whatnot. And that's really not the case. I mean, it'll tell you in general where problems may be, but you still have to, let's say it said fail, you still then have to look at this guy, understand it, and work your way through the logic in the address decoding logic or some other logic to figure out, okay, now what's the problem? So it is a tool, but you really have to understand not only how to use it, but what to do with the information that it gives you. So, side step there. One thing that I noticed right off the bat, as soon as I hooked up the Fluke, playing around a little bit, is the NVRAM doesn't seem quite right. It starts at C000 to C3FF. So if I just do, let's just say I want to read what's in that RAM. I'm going to read from C000, and it comes back with FF. Now let's say I repeat that. Now it's E5. You zoom in so you can see it here. Now it's FF again. Now it's 3B. So, I mean, if the memory was fine, this number should stay constant. In fact, I should be able to write a value to C000. And let's say I want to write AA. Illegal. Oh, I'm sorry. Oh, that's my mistake. Okay. Write to C000 AA. Okay, so let me read that back. C000. Yeah, 77, not AA. So there's something sketchy going on with the NVRAM. So what does that mean? It means I have to now find the NVRAM on this guy, and then start at the address circuitry leading up to the NVRAM, making sure that's working okay. If it is, then look at the data path from the NVRAM back to the CPU and look at that. Is that okay? So that's kind of the painstaking process of figuring out. That's all the video schematics right there. Of figuring out what the problem is. So, but that's where we are. At least we know that most of this other stuff is okay, and we'll dig into the NVRAM and see if we can figure out what's going on. Okay, so I took a look real quick at that non-volatile RAM. It's this guy here, and notice that the write signal wasn't toggling, and which is odd because the write signal that goes to this guy is the same that goes to the other two RAMs here. And so I took a look again at some of the other signals, the reset for the CPU, and particularly the watchdog timer circuitry. And looking at the schematic here, it's up in this area. And I noticed that there's no clock getting sent to the watchdog timer circuitry. And that guy comes from the video blank signal. Video blank signal is generated from the video PCB. And so there may not be anything wrong with the RAM. Rather than go down that path and try to figure out why the write signal is not toggling, I think I'd rather first figure out why isn't the watchdog barking, because that could lead to what's causing this over here to happen. So let me start with that. I'll take a look at the video generation circuitry on this schematic here, figure out what's causing video blank not to toggle, and hopefully we'll be able to bring some light back into this guy. So. Alright, so open up the stack here so that I can have access to the video PCB. The main CPU PCB is on the other side, and that's, I think, the background PCB. Anyway, I think last we saw the horizontal blank signal, the V blank signal wasn't getting driven properly. And I took a look at this board, the video board, and the clock is completely gone. And it appears to be, if you're following the schematic, it's up in this area. The clock is generated here through the crystal, runs through here, and then goes through a bunch of these buffers here. Buffer is located up here at 2B, and if we look at the input to the buffer, let me see if I can hold this here while I do this. So there's the input to the buffer, and the output of the buffer is there. Notice the light doesn't change. Like if I ground something, it gets dark. If I grab a VDD, it should get brighter. You can kind of see it. I know my finger's in the way. Let me try it like this. Yeah, see how it gets brighter? If it's tri-stating, if it's not getting a valid high or low, it's in the middle, the light shouldn't change at all. You can see it kind of flashes just for a second, but then it doesn't go anywhere. So these are actually tri-statable buffers, although the enable is grounded, so they should be active all the time. Check the enable here. Yeah, the enable is grounded there. Right there. So it should be driving all the time, but it's not. So again, there's our input and there's our output. So a huge section of this board, if not the whole board, has no clock. So that's obviously a problem. So we're going to replace this guy as a starter and then see if other, if it comes right to life, or if we've got other problems, then we can tackle them as they come up here. So stay tuned. Okay, before I replace this buffer, I just wanted to show off this new tool that I got. It's called an eComms bug trap, or a TTL comparator. And basically what it does is you attach it to a TTL IC, in this case it's the buffer that we're going to look at, one of these chips that you think might be wrong, and then you take a copy of that chip and put it in here. So in this case it's a TTL, it's a 74 367 I think, and which is a bus driver. So I have a known good one in here, and this one is one I suspect is bad. And what it's going to do is it's going to compare, it's going to drive the inputs to this guy the same as this, and it's going to compare the outputs. And if any of them are off, then it'll indicate it with these LEDs here. So this is actually the first time I've tried this thing. I just got it, well, didn't get it recently, but this is the first time I've actually fired it up. So let's fire it up and we'll see what we get here. Aha! Okay, so as we suspected, pin 5, which is, I think, that output that we were looking at. Yeah, that's the clock output. Actually, I'm looking over a schematic over my shoulder here. That's the clock output that we were looking at that was non-existent. And then we actually have another one over here, 17. I'm not sure what that is off the top of my head. I don't see it on the schematic here as I'm looking over my shoulder. So, but there's our guy right there. So, I mean, we verified it with the logic probe that it was gone, and I was just ready to rip it off. But as I was going through my drawers here, I found this guy and forgot I even have it. So I figured I'd fire it up and just kind of give an overview of what it does. So. What's nice about this too is it has a latching feature. So let's say one of these guys is right 99.9% of the time, and then there's just something quirky about it. Maybe it's starting to go or something, and then all of a sudden, you'll get a little glitch or something will miscompare. And that's usually what causes those weird graphic glitches sometimes. And when you're playing a game, almost all the time it's fine, but every once in a while the sprite gets all scrambled or something looks off. So this thing will keep track of that, and if one of these fails, even for an instant, it'll latch this LED so that you can go back and say, oh, okay, so yeah, there is something going on there, and then you can replace it if you feel confident. So what I'm going to do is I'm going to throw this guy here on the workbench, the rework bench, and desolder this guy and throw this guy in there. So, and then we'll fire it up again. One quick note: whenever I do replace an IC, I always replace it with a socket. That way, if the IC I throw in there that I think is good is not, then I can easily pull it out and throw another one that I assume is good in there in its place, and that way I don't have to unsolder the whole thing and just go through that whole step again. So they're worth pennies. I mean, they're only a couple cents, so but it definitely saves your time and the odd chance that you might throw in a bad IC. Okay, so we got our chip in there, our socket, back on the bench here. Let's turn this guy on, and ooh, we've got something. Dip switch. Alright, let's see if we can put this out of test mode here. Hey! Alright, looks like we're in business here. Seems to be running up okay. Let's check the other monitor. Actually, we'll let this one switch over. I think there we go. And if I switch it over, there's the Hall of Fame. So graphics wise, I mean, so far I'll let it run for a while, but things seem to be looking good. And then I'll hook up the speaker here, and one of these days I'll have to mount that permanently. But we'll hook it up and make sure everything's working okay. Looks like the enemy sprites and player sprites are okay. Background graphics are okay. Characters are down over there, looking good. So yeah, I'm pretty optimistic. I think we're going to be in good shape here. So yeah, very cool. Another one brought back from the dead.